Hi, I'm Brian Mullen, and this is Balls Out Physics, Episode 1, Planes Flying on a Spinning Ball. About 7 months ago, or well, 8 months ago, beginning of the year on New Year's Day, I went and saw Interstellar, and I thought it was awesome. And it got me to go back and read this book for probably about the third time in my life, What is Relativity? It was written in 1959. Really good book, very good explanation of relative motion. From planes moving across the Earth with balls bouncing inside them all the way up to things traveling at the speed of light. It gives a really good explanation of Einstein's theories. And so, here I am, my head in the clouds, thinking about relativity and space travel and all this craziness. And I was, just bored one day, sitting on the couch, looking through YouTube videos, and a couple flat Earth conspiracy videos popped up in the that suggested videos to watch, and I'd seen those before, and I always had thought to myself, there's just no way, But I'm a very open-minded person, and I was in the mood to watch something different, so I said, what the heck, I'll watch one of these, thinking it would be good for a laugh. Well, about halfway into it, I wasn't really laughing. I was actually questioning a lot of things. One of the biggest things that caught my attention was planes flying on a spinning Earth, trying to land on north and south runways. Because the Earth rotates from west to east, and things don't seem to line up based on the examples they were showing. This was all graphically, and so I started to look into this a lot. And what really surprised me at first is, I'm a structural engineer, and I've taken a lot of physics courses in my life. And I started to look into the curvature of the Earth and the rotation and the speeds of Earth, and it kind of blew my mind that I've never really thought about how fast the Earth rotates or how much it actually curves. Here I am researching flat Earth theory, and I'm actually studying the curvature of Earth and the speed at which it rotates. I mean, there's some serious irony there. Our Earth, our model shows it spinning from west to east around an axis, which is represented by this little stick, and the circumference of the Earth at the equator, right here, is, the circumference of the Earth is 24,901 miles. So at the equator, since that's the farthest point from the axis of rotation, and there are 24 hours in a day, the speed of the Earth is 24,901 miles divided by 24 hours gives you 1,038 miles per hour. That's the instantaneous velocity at any point along the equator. I mean, that's what it has to be if everything we're told is true. So that's really fast. That's faster than the speed of sound, which is Mach 1, 761 miles per hour. So I never really thought about how fast that is. I always thought just kind of assumed it was moving really slow, and you didn't really think about how much distance has to be covered in one day. But I also had never thought about or even calculated how much it actually curves. The general accepted value is 8 inches per mile, and I mean that's what it has to be based on the circumference, and that's 8 inches per mile, varying with the distance squared, because if you're standing, or if you're on a point that's just above the surface of the Earth, or just on the surface of the Earth, and you look straight out away from you, across water, of course, because land has mountains and all kinds of things, but going across the surface of water, at the first mile you would expect to see an 8-inch drop down to the curve. And at the second mile, because it's a curve curving down, it's continuously getting farther away from that horizontal line that you're driving, that you're sighting out away. The second mile is 8 inches times 2 miles squared, which is 32 inches. And then third mile is 8 inches times 3 miles squared, and if 3 miles squared is 9, it gives you 72 inches. It starts to drop off pretty quick. And so I'd found that the Flat Earth community had created this. Someone out there did this. This is a curvature chart. The Flat Earthers are making a curvature chart, and they're showing how much curvature would have to be, we would have to see in all directions, because it's a sphere, anywhere on Earth. And this was drawn in AutoCAD, and since I'm an engineer, I have access to AutoCAD. The first thing I did is I went and drew a circle with a radius of 3,959 miles, which is the accepted radius of our Earth. I converted that to feet, which comes out to over 20 million feet, and started plotting points and finding that this is very accurate. This is exactly what you get. So I'm starting to wrap my head around how much curvature there should be, and that's quite a bit. And it's kind of hard to find it. So anyway, one of the first things I did is I set up a problem about the spinning planes. It was a physics problem. I studied relativity. I figured I could do this. The idea of this problem is that we are an observer, a stationary observer, looking at Earth, watching a plane fly. And this is based on a direct flight I took in college from JAX to LAX. The two airports are about 2,000 miles away from each other. And I flew there and then flew back, and I like doing the problem going back because it's more interesting that way. Because we're rotating with the Earth, and also a lot of some flat earthers out there have said things like, if the Earth is rotating 1,000 miles per hour at the equator, planes can't fly that fast, so they can't catch up to it, and that's not really true, because if the plane's already rotating with the Earth when it takes off, the speed it gains in the air is added to the initial speed it already had. So that's not true. But there is a problem here, and that's what I want to get into. So these two airports are 2,000, here's my dimension line here. They're 2,000 miles apart, roughly. And we're just going to say they're 2,000 miles apart in order to keep this simple. Okay? And they're also, they're not at the equator. They're north of the equator. A little over 2,000 miles, both of them. Jacksonville's over here in Florida, and LAX is over here, California. LAX is about 250 miles north, I think 250 miles north of JAX in Jacksonville. But we're going to say that they're at the same latitude, just to keep it easy, to keep the problem easy. And so, as I was showing you on the ball, as you move up away from the equator, the diameter of the Earth around the center axis decreases, so your velocity decreases. You can calculate this, and I played around with some numbers, and I got between 850 and 900 miles an hour for both airports. So I just said let's just use 900, just to keep it easy. It's a hypothetical problem, but it is based on reality. So the reality we're all taught to believe. So here we are. We're going to fly back to JAX. Sitting on the airport in LAX, we're going 900 miles an hour east. The Earth is moving that fast, but we can't feel it because everything's stuck to it, right? So we're told. So the plane takes off and gets up to its cruising altitude, whatever that is for the day, 30,000, 33,000 feet, whatever they're going to fly at. And it gets up to a cruising speed of, let's say, the velocity of the plane, VP, equals 600 miles per hour. Now, since it was already moving, the velocity of the plane relative to Earth, which we'll call VPE, is now 600 plus 900 miles an hour gives us 1,500 miles per hour. This thing's really moving. Okay, but it's relative velocity, so it only seems like 600 miles per hour to us on the plane, right? That's the theory. So everything makes sense. We're moving fast, 600 miles per hour faster than the Earth is spinning, so we're moving towards Jacksonville. But here's where we run into a problem. Let's say there's a north-south runway in Jacksonville. Now Jacksonville's runways are actually orientated kind of 45 degrees northwest and northeast, but north-south runways do exist. You can go look on Google Earth, you'll find them. They're all over the place. And of course, LAX's runways all point east-west, and they're right on the water, or right on the ocean. So we get up here to this point, right before they make the turn, the plane slows down. Okay, this is where the problem comes in. Planes cannot stop flying before they make a turn. They can't go to zero, and going to zero would bring you back to 900 miles per hour that you started at. But you can't go to zero because a plane has to keep flying forward to have uplift on the wings and keep itself in the air. Duh. So it's going to slow down before it makes the turn, but it's not going to zero. So let's say it slows down to 300 miles per hour. You know, and then it also that's the speed it slows down to before it makes this 90-degree turn, or this right angle turn. So here, the plane, right before it makes the turn, is traveling at VP prime equals 300 miles per hour. Now, VP prime is just the new speed, okay, or the new velocity in this direction. But it's also got its relative velocity to Earth, which would be VPE prime, is now 300 from 1500 is 1200 miles per hour. So now, as this plane goes through the turn, when it gets here, say the midpoint of the turn, it's got a vector of 300 miles per hour, which is its airspeed, this VP prime in this direction, but it also still has this velocity of VPE prime right up here, 1200 miles per hour. It doesn't lose that velocity. It can't, because the Earth is spinning under it. You know, and it had that initial speed when it took off. The only way you can get rid of that is if you make the Earth stop spinning. So, you know, when you get down here and you're trying to line up with the runway, you're going 300 miles per hour towards it. Make that look a little better. And you still got VP prime here, but you also have VPE prime. Well, there's a real problem there, because the airport, the ground over here, is moving, you can see that, at 900 miles per hour. You know, we said the velocity of the Earth is the same at both airports. But the plane is moving to the east still at 1200 miles per hour. The plane is moving faster than the runway. They can't line up. What you actually get, if you draw this point over here, actually let's erase this and do it right here where we started. What you would actually end up with is a path that looks like this. More of a linear path, because the plane, you know, this point represents the plane. The plane has a vector this way and another much larger vector this way. So you're getting something like that. The plane is actually sliding sideways through the air. That doesn't make sense. I mean, it's kind of what's going on. You know, this question, of course, people say, well, the atmosphere, this is what I thought too initially, the atmosphere is moving with the Earth. So, you know, since the atmosphere is moving with the Earth, you know, it's like a fluid that you're traveling through, so it doesn't matter that your initial speed was 900 miles per hour, and then you have a relative speed, and that doesn't work. When you really start to think about it, it doesn't work. You know, the best example I got from another engineer I showed this problem to was, he said, what about a fly on a train? You know, the train, the air in the train is moving with the train, and the fly can buzz all around inside the train. You know, you've probably seen bugs in a vehicle before of some sort. You know, and the fly is unaffected by the movement of the train. Well, first of all, a fly can hover, which a plane can't do, and also the air in the train is contained within the shell of the train. Earth does not have a shell that, at least so we're told, that contains all the air. You know, the space shuttles and rockets and everything flies through it. You know, they leave the Earth. What's supposed to hold our atmosphere to our Earth is gravity. So we're told, you know, air actually still has a mass, and so gravity pulls. You know, anything with mass exerts, as we're told, anything with mass exerts a force on anything else with mass, like they attract each other. I'll get into that in another episode, because that's also a big issue I'm finding. But so the atmosphere, you know, spinning with the Earth, you know, wind blows in all different directions. It's not constantly blowing from west to east, because if it was moving with the Earth, it would be blowing from west to east, and that wouldn't help us at all, because, you know, the plane is also going from west to east. So if anything, the atmosphere is just pushing it along. It's not helping slow it down. If you reverse the problem and go the other way and flip the runways around, which is what I initially did, you end up with the plane going 300 miles per hour too slow. And of course, if the atmosphere is going from west to east, then maybe you could say that the atmosphere pushes the plane back up to that velocity. But, you know, Newton's first law says that an object in motion stays in motion unless acted upon by an outside force. So an object in motion relative to another object in motion stays in motion relative to that object unless acted upon by an outside force. It has to. The atmosphere doesn't answer the question. And the other problem with the atmosphere is air gets thinner as you get farther away from the Earth. So the gravitational pull on the air as you get higher and higher is less. So by conservation of angular momentum, air at higher altitudes would have to be spinning slower. And this, this is where, the actual concept of dark matter comes from in galaxies, because stars at the outer edges are spinning at the same speed as stars in the inner ring of the galaxies, and so we say there's more mass there to make up for this, and that's another thing I'll cover in a coming episode. But there's no real answer for this. So I started thinking about this. I'm trying to visualize this, because we never do problems like this, in my engineering classes in college, we used to break down, we derive equations, calculus. We use calculus to break down equations that somebody else had already derived before, and I always thought it was annoying because, it always comes down to a simple algebraic expression. Everything in our world becomes very simple. It's kind of amazing. But, everything breaks down to a simple algebraic expression. We go through all this proof to back check what these guys had done. But never did we back check our theory of living on a spinning ball. Ever. We don't do these problems. Why? Why don't we talk about the curvature? Why don't we talk about the velocity? I went back to school and took astronomy in 2013, and we kind of talked about this, but not in depth like this. And then the other thing I started to think about is, I live in Central Florida. I heard a sonic boom one time from supposedly the space shuttle landing. Rattled my windows and doors. It woke me up, scared the crap out of me. It was pretty awesome actually at the time. The landing strip for the runway at Cape Canaveral is north-south. The north end actually points a little bit to the west, this way. Actually, west is actually this way. But it's mostly north-south. And I also have seen space shuttles take off from the beach. I accidentally saw one. I just happened to walk out on the beach up in Jacksonville one time and saw one take off. And I saw it go out over the water, going to the east, which would actually be this way. Going out over the water to the east. And then it disappeared from my sight. I thought it went out into space. So it's rotating with relative to the rotation of Earth. Definitely. And when it gets up into space, it's still going to have those components. It's adjusting with we're told it adjusts its movement in space with air jets. Spraying mass out into nothingness, which I'm also going to do another episode on, because that doesn't make sense either. But we'll get into that too. So now this shuttle is going to re-enter the Earth's atmosphere, traveling at thousands of miles per hour when it comes back in, and it's supposed to come back in gliding. It comes through the atmosphere, and you've seen all the videos where the fuselage heats up, and it's slowing down, of course, as it's coming into our atmosphere. But if this thing is coming in at thousands of miles an hour, and trying to come in from either the north or the south end of that runway, and it definitely has components of velocity to the east or west, and that runway is spinning somewhere between 850 and 900 miles per hour to the east. This is insane. The little jets that shoot to the side and the shuttle aren't going to do anything in our atmosphere. This is insane. It doesn't work. Really, try to think about this. Try to wrap your head around an Earth spinning. In all the movies we see of space, the science fiction movies and everything, whenever like a ship is coming up on a planet, the planets always seem to be stationary, because if they were actually rotating at the speeds they would have to be rotating for the length of their days, whether it's Earth or another fictional planet in a movie, it would probably hurt our heads to have to see the ships and things rotating like that. So for Hollywood, and then to make things easier, we see it stationary. It appears stationary. Of course, you could say it's moving too slow, but it's actually moving pretty fast. So, Earth is at least. So anyway, here's the spinning ball problem, but we also still have the curvature problem here. We're flying a great distance, 2,000 miles, and based on that curvature chart I showed you earlier, there's a lot of curvature that this plane has to fly over. So, in the architecture and engineering world, looking down on something is called a plan view. So we call this a plan view of Earth. And we cut sections through our plan views to look at a section through a building or anything we're designing. So what if we cut a section through the Earth here? This is typically what a section cut line looks like, something like this. Okay, so we're going to cut a section and turn our view, up, looking into the plan view. Okay, so let's draw that. Still 2,000 miles apart. from here to here and say this is LAX over here and this is JAX over here. Both airports are roughly at sea level. I mean, LAX is right on the water and JAX is a little bit inland, but I mean, Florida's flat, so it's basically at sea level. So we've got this curve of the Earth, the amount of curvature that we would see over 2,000 miles. And here is our datum line, which is sea level. Okay, so this is LAX, this is JAX. Okay, so this distance here, let's get something, use a different color for this. This distance here to the curve would be based on 1,000 miles an hour, 1,000 miles of distance. Excuse me. I mean, this is rough because where do we actually measure? Do we measure across the curve, or do we measure the distance between the 2 points? You know, miles are linear measurements, but we'll just ignore that and just keep it simple and say 1,000 miles. Now you take the curvature chart, you look on here, see if you can see 1,000 miles. 1,000 miles. The height of your curve at 1,000 miles should be roughly 128.4 miles. All right, so this distance here is 128.4 miles. Okay, our plane takes off, you know, heading this way, I guess, because it has to follow the curve, and it gets up to about 30,000 feet, 33,000 feet. That's 5 miles. That's a mile is 1 mile is equal to 5,280 feet. So now you're up here somewhere, and you're trying to fly over here, like this, I guess. I mean, you can't fly through the Earth like that, so you still have to follow the curve, obviously. Well, this plane is flying along and follows this curve, right? The Earth is constantly curving, so the plane constantly has to be following the curve. Well, that's a problem because when the rudders on a plane are straight, the flaps or rudders, whatever you want to call them, they're called rudders because it's just like a boat moving through water. Air is a fluid, really, and so when you turn a rudder on a boat, it controls the direction of the boat. Just the same thing in the air. When plane turns its rudders on the wings or on the tail, it affects its motion through the fluid, but this is the atmosphere that's flying through, and it controls its orientation and where it's going. So, to follow this curve, the plane would constantly have to nose down. The pilot would constantly have to nose the plane down if that's how a plane flies. When I first thought about this, I'm like, that's crazy. The Earth is constantly curving, so it constantly has to nose down to follow it. So I got on the internet and started looking up explanations for this. People have asked this question before, obviously, and the general accepted explanation for this is that gravity does it. It's basically like it's going into orbit, and because you have that force, you have this force of gravity on the plane pulling towards the center of the Earth, it makes you follow this orbital path. It's like a ball on a string spinning it around. The force in the string pulling it towards the center makes it actually rotate around. I mean, that's where the theory of all of our orbits in space comes from, is that force pulling towards the center of mass. All right. But see, there's a problem with that because the rudders on the plane are not the rudders, the rudders, elevators, whatever you want to call them, they're straight, but we're following a curve. Okay, so even though the pilot's holding the controls or autopilot or whatever, I mean, they're making little adjustments here and there, but I mean, basically, you fly up and you level off. You feel that when you fly on a plane if you've ever flown on a plane before. So, what if? You said gravity is the explanation for that. I said, okay. I started thinking about it. That makes sense. I thought about things orbiting Earth, but what if the pilot? Let's draw a plane again. Say up here somewhere. What if the pilot decides he doesn't want to follow the curvature of the Earth for some reason, and he wants to follow a point, a line that is tangent to the Earth, like this, a straight line. So, the pilot wants to follow that line and not fly, he kind of wants to fly up relative to the curve, I guess, or down, depending on which way you're looking at it. But, so now he's got this force of gravity that's trying to make the plane follow the curvature of Earth, based on the accepted explanation for what I was talking about before. So, if you want to fly in a line that's tangent to a point, on the Earth, then you have to fight that force of gravity that's trying to make you follow the curve. So now it's the same problem in reverse. Now you constantly have to pull up on the controls or nose the plane up to fly in a straight line. You know, with the rudders, you know, you're cutting through the air, but you're flying in a straight line with the rudders actually angled like this to make the plane fly straight. That doesn't make any sense. This doesn't work. That's not an explanation. Gravity is not doing this. You know, where's this curvature? And you know, when you fly in a plane, you know, you'll notice when you look out the window, the horizon, of course, looks flat, and we're told that, you know, the Earth is too big and we can't see it, and it's also at eye level. You know, if there's really a curve, there should be a drop. Now this one, you know, people argue about this one. It's a big argument in the flat Earth, round Earth community, but it's becoming a huge debate on the internet. More and more people are waking up to this. It's pretty amazing. And you know, what we're not taught in school is, you know, in the late 1800s, there was a raging debate going on between, you know, flat earthers and globulists, as they were called. You know, people still believed that the Earth was flat. Well, you know, Columbus didn't sail to America and prove, and everybody just started believing the Earth was a ball. A lot of people didn't believe it, and there's actually I've read some testimonies from civil engineers in the 1800s that just say it's ridiculous. You know, when they're talking about laying train track and all kinds of things. So I'm at a loss here. I don't know what to think. I mean, I'm kind of thinking it's flat and stationary. I've gone to Lake Apopka and I've taken my telescope there, and on the south end of the lake, you know, Lake Apopka is one of the biggest lakes in Florida. I think it's the second biggest. On the south end of the lake with my telescope sitting 3 feet above the shore, I can see the North Shore 8 miles away. Well, based on the curvature chart, there should be, what is that? Based on 8 miles, I should have a 43-foot drop from one side to the other. I shouldn't be able to see the shore. You know, there should be a curve of water in my way. I mean, you can't see it on a rough day when the waves are in the way, but on a calm day, you can. That doesn't make sense. I should not be able to see that. So, I don't know what's going on here, you know. I've had my world turned upside down or right side up by this. I've spent a lot of time researching this, you know, a good 7 months, and I've seen a lot of different things. There's a lot of topics to talk about, but this is the one I thought I'd start with. So, I mean, you guys out there, you can leave comments, call me crazy if you want to, but you got to give me an explanation for this if you're going to call me crazy, and, you know, help me out here. I'd love to go back to believing that I live on a spinning ball, and if this isn't some massive conspiracy and we all haven't been duped, but human beings are very easy to fool. And it's actually much easier to fool a human being than to convince a human being that they have been fooled. You know, we come into this world, we don't know where we come from, we don't even know how our thought process actually work. You know, we don't know how we're able to simultaneously create thoughts and perceive them at the same time. You know, we still can't explain that. So what do we really even know? Anyway, that's getting off topic. This is episode 1. We'll be getting into more. I'll have many more episodes after this, hopefully. So, until next time, peace. Hi, I'm Brian Mullen, and this is Balls Out Physics, episode 1, Planes Flying on a Spinning Ball. About 7 months ago, or well, 8 months ago, beginning of the year on New Year's Day, I went and saw Interstellar, and I thought it was awesome. And it got me to go back and read this book for probably about the 3rd time in my life, What is Relativity? It was written in 1959. Really good book, very good explanation of relative motion, from planes moving across the Earth with balls bouncing inside them all the way up to things traveling at the speed of light. It gives a really good explanation of Einstein's theories. And so, here I am, my head in the clouds, thinking about relativity and space travel and all this craziness. And I was, just bored one day, sitting on the couch, looking through YouTube videos, and a couple flat Earth conspiracy videos popped up in the, that suggested videos to watch. And I'd seen those before, and I always had thought to myself, there's just no way, But I'm a very open-minded person, and I was in the mood to watch something different, so I said, what the heck, I'll watch one of these. I think it would be good for a laugh. Well, about halfway into it, I wasn't really laughing. I was actually questioning a lot of things. And one of the biggest things that caught my attention was planes flying on a spinning Earth, trying to land on north and south runways. Because the Earth rotates from west to east, and things studying the curvature of Earth and the speed at which it rotates. I mean, there's some serious irony there. Our Earth, our model shows it spinning from west to east around an axis, which is represented by this little stick, and the circumference of the Earth at the equator, right here, is, the circumference of the Earth is 24,901 miles. So at the equator, since that's the farthest point from the axis of rotation, and there don't seem to line up based on the examples they were showing. This was all graphically, and so I started to look into this a lot. And what really surprised me at first is, I'm a structural engineer, and I've taken a lot of physics courses in my life, and I started to look into the curvature of the Earth and the rotation and the speeds of Earth, and it kind of blew my mind that I've never really thought about how fast the Earth rotates or how much it actually curves. Here I am researching flat Earth theory, and I'm actually